Hello. So today what I'll be doing is first we'll be going over Taylor polynomials and in particular the error for the Taylor polynomials using the Taylor's inequality. So I'm going to start with this question. So find the second degree Taylor polynomial of cube root of x centered at x equals 8. So i.e. p2 at 8x. So to find the Taylor polynomial, what we need is, so a Taylor polynomial, or p28, that's the better way to, p2 at 8x, don't like my size, okay, there you go, p2 at 8x is equal to, so a Taylor polynomial, what happens here is that you have x plus f prime at x plus f double prime. Oh, and I forgot to add something, obviously. So x minus x now plus f double prime x times x minus x now squared over 2 factorial. And that's for the second. So that's just if we're going for the second. If we would go for the third, that pattern would continue. So let's just start with what we have. So as we see here, what we need to do is we're going to need to find f prime at x. So what do we have? We have the cube root of x. So that is equal to f of x. F of x. So then f prime at x is equal to 1 over 3 times x to the power of negative 2/3. 2/3. And then f double prime at x is equal to negative 2/9 times x to the power of negative 5 over 3. So then, because we are centering our x, we're centering it around 8, what we're going to do is we're going to have to evaluate these at x equals 8. So f at x, f at 8 is equal to 2. So cube root of 8 is just 2. Then f prime at 8 is equal to 1/3 times 1 over cube root of 8 squared, which is just equal to 1/3 times 1 over 4, which is then equal to 1 over 12. And finally, f double prime at 8 is equal to negative 2 over 9 times 1 over cube root of 8, cube root of 8 to the power of 5, which is then equal to negative 2 over 9 times 1 over 32, which is then equal to negative 1 over 144, because you're going to get 9 times 16. So perfect. Now that we have all our values for f primes, what we can do is we can go back to our original formula and fill everything we have. We need it. So then our original x is equal to 2. So then it's going to be 2 plus f prime at x is 1 over 12. So it's 1 over 12 times x minus 8. So then we're getting at negative 1 over 144. So then it's going to be minus 144, 1 over 144 times x minus 8 squared over 2 factorial. And there you go. And if you want, we can obviously simplify this a bit more and make this 288. But that would be our Taylor polynomial for the cubic. So the cube root function centered around 8. So, and it would be of second degree. That's what this 2 stands for. Great. So now the second question then is, use Taylor's inequality to find an upper bound on the error, expressed as a fraction, and using p over p, the Taylor polynomial of second degree centered around 8. And then use it basically to approximate the cube root of 10. So then, to find, let's leave this on the screen, right over here. So then, to find the error of a certain function or a certain Taylor polynomial, we use the Taylor inequality. So the Taylor inequality, you have f to the n plus 1 of x times x minus x null to the power of n plus 1 over n plus 1 factorial. So your error is always going to be smaller than this. And sometimes this part over here, the n plus 1 derivative of our f, this is also sometimes referred to as k. You can also view it as k. So this can also be viewed as k. And what's important to notice is that all of this is basically in absolute value signs, just to know. And this can be kind of useful later on. And this is also an absolute value. So then what we need to do is first we need to figure out the fn plus 1 derivative. And we always need to maximize. So I'll talk more about maximizing later, but you need to consider that we want to see what the maximum error bound is. Because if we say the smallest error bound is 0, so we get a perfect approximation, that doesn't help us. Because if the maximum error that we can make is 1,000,000, then just knowing that it's in the range of 0 to 1,000,000 is like, that's already useful because again, you need to know the upper error bound. Because if it just can be anywhere from 0 to infinity, then that doesn't really tell you anything. So that's why we're always looking for like an upper bound. What's the biggest error we can make? Because the smallest error is obviously that we're perfect. So first, let's start by finding k or fn plus 1 derivative. So in this case, because our degree is 2, what we're looking for is our third derivative. So before, if you remember right over here, we had our second derivative. So just over here, I'm going to continue and find my third derivative. So f triple prime at x is equal to 10 over 27 times 1 over x to the power of 8 over 3. So I'm just going to quickly copy that down and bring it over there so it's a bit closer. Control C. And I'm going to bring it right over here. Control F. Perfect. Let's move this just a bit over here. Great. So we have our n plus 1 derivative. So now what we need to figure out is how can we maximize this, make this the biggest possible in our interval, you could say. And to do that, because we know right now that our interval is 8 to 10. And the reason we know that is because what we're trying to approximate is we're trying to approximate the cube root of 10. So in essence, our range is from 8 to 10. So now we need to pick a term in our range to try to maximize k, to think of what our biggest error can be. So now what we need to look at then is our function. And what we can see is our function 1 over x to the power of 8 over 3 is a decreasing function, right? The bigger x gets, the smaller our f of x is. Or in this case, it's f triple prime x, but this function itself is a decreasing function. So what we get then is that to maximize this, to make this the biggest it can be, we need to take the value at 8, because 8 comes before 10. And so at that point, this will yield a bigger value. So that's why over here, what we're going to do is we're going to plug in 8 as our x. So we're going to get equals to 10 over 27 times 1 over 8 to the power of 8 over 3, which is then equal to 10 over 27 times 1 over 2 to the power of 8, which is then going to equal to 5 over 3,456. So cool, we have our k. We know that our k, or this value over here, is always going to be smaller or equal to 5 over 3,456. But again, because we want or to see what the biggest error is, we're just going to set this to 5 over 3,456 because this is the biggest value our k can take. So then what we're going to look is we're going to look ahead and we are going to see, so if we plug this in instead of our k, we're going to get 5 over 3,456 times x, our x null is 8 because we are centering it at 8. So x minus 8 to the power of n plus 1. So in this case, our n is 2. That was our order of the polynomial. So if we plug in 2, we're going to get 3 to the power of 3 over n plus 1 factorial is going to be 3 factorial. And now we're kind of at a roadblock again. We have this variable over here. So now again, we need to think, what x can we put in there to maximize the error we can have, to maximize this number? So if we plug in 8 over here, we're going to get a 0, and all of this is going to become 0. So that's kind of the smallest possible value we can get. To get the biggest value we can get, what we're going to plug in is 10, because 10 minus 8 is going to give us 2, and that's going to give us our biggest value that we can, to again see our biggest error. So finally, if we plug in 10, we're going to get 5 over 456 times 10 minus 8. We're going to plug in 10 because that's the biggest value. 3 factorial. So then, using this, we're going to get the biggest possible error that we can get because in each step, we maximized the value we're getting. So then, if we simplify all of this, what we get is 5 over 2,592. And so this then tells us that that's our biggest error. So when we actually use the Taylor polynomial to try and figure out what cube root of 10 is, then this is the biggest error you can get. And you can check this by using this Taylor polynomial. So you can use this Taylor polynomial and plug in 10 there and see what value you get. And then you can plug into your calculator and you can see that you're actually going to be within this much, which is about 0.002, about this much or 0.002 away from the actual answer. Okay, cool. Let's do another question. So our next question is let t of n of x, so let t n of x, or Taylor polynomial of x, of degree up to n, so we're going to have a degree up to n, have for y equals sine of x equals sine of x, expanded about 0, so we're having it around 0. We're centering our Taylor polynomial around 0. Find an n such that absolute value of sine at 0.1 minus our Taylor polynomial 0.1 will produce or give us an error smaller or equal to 10 to the power of negative 6. So basically what we're looking for is at what degree n of our Taylor polynomial will our error become smaller than 10 to the power of negative 6. So the way that we can approach this is, first, as always, we're going to have to look at, because the way we find our error is, as we saw before, we fn plus 1 x, so the nth plus 1 derivative of f of x, times x minus x null to the nth plus 1 derivative over n plus 1 factorial. So our first step, as always, is going to be to find this term, basically. As I said, it can be called k, but it's the nth plus 1 derivative. So what we're going to do is we're going to kind of take the derivatives of sine x. And so what do we know of sine x? That its derivatives are, there's a pattern to them. And I'm just going to write out this pattern so that we can draw on a conclusion a bit later. So the derivatives of sine are cos. After cos, it's negative sine. After negative sine, it's negative cos. And after cos, again, we get sine. But what we see for all of these values that the max value that you can get out of them when you're thinking about it is 1. So no matter which one of these you land upon, the max value you can get is 1. So this f to the power of this nth plus 1 derivative, f of to the nth plus 1 derivative, not to the power of, but it's like the nth plus 1 derivative of f of x, it's always going to yield the highest value of 1, right? So then what is going to happen is that we can kind of already plug this in there and see that. So then what happens is, so we know that this, it becomes 1. So then get 1 times x minus x null n plus 1 over n plus 1 factorial. So now what we're going to think of is that this general formula is if you were just thinking of your f of x. So if we have f of x minus tn at x, the absolute value of this is going to be smaller than all of this. So the fn plus 1 derivative, or the error in essence, this is what it's saying. The error is going to equal to the fn plus 1 derivative, fn plus 1 derivative of f of x times x minus x null n plus 1 over to the power of n plus 1 over n plus 1 factorial. So in this case, our polynomial is centered around 0, and we're trying to find the error for 1.0, or 0.1 to be specific. So then our x null is 0, and our x, to maximize our value, and in this case our range, you can think of that is from 0 to 0.1. To get this to maximize this bracket over here, you're basically going to be plugging in 0.1, and 0.1 minus 0 is 0.1. So then again, what we get is we can fill in like another factor here, and that is that we're going to get 1 times 0.1 to the power of n plus 1 over n plus 1 factorial. Now, what you can kind of see is that we're going to be dealing with 10 over here. So 0.1 is 10 to the power of negative 1. So to kind of make it simple for yourself, you can also rewrite this as 1 over n plus 1 factorial times 10 to the power of n plus 1. So basically, because it's 10 to the power of negative 1, it becomes 10 to the power of negative n plus 1. And then that can just go to the bottom. So now we have this. So then what we know is that this 1 over n plus 1 factorial times 10 to the power of n plus 1 has to be smaller than 10 to the power of negative 6, because that's what we're trying to find out. What n is this going to be smaller than 10 to the power of negative 6? Or past what n is this going to be smaller than 10 to the power of negative 6? So then we get smaller or equal to 10 to the power of negative 6. Sorry. So then what we're basically going to do is we are going to start and try to solve this. So then by manipulating this, we can get that n plus 1. So basically, if we take 1 over both of them, we have to flip the sign. So we get n plus 1 factorial times 10 to the power of n plus 1 is bigger. So we're kind of taking the opposite than 10 to the power of 6. So again, we're just taking the reciprocal of both of the sides, and that's why we have to flip the sign. That's how we get this. And at this point, what you kind of do is you can kind of think of it as guess and check. So for sure, you know that if n is equal to 5, you're going to get something bigger on this side, because you're going to get 10 to the power of 6 times something, and that's obviously going to be bigger than 10 to the power of 6. So n to the power of 5, at n to the power of 5, you're definitely already going to be within, like, your error is already going to be smaller than n to the negative 6. What you can then do is you can just kind of start checking then below. So if you get n equals 4, then you're going to get 5 factorial times 10 to the power of 5. Now, is this bigger than 10 to the power of 6? Yes, in fact it is, because 5 factorial is 120. So you're going to get a couple of more, you could say, powers of 10 there. So that would work out. But then if you try plugging in 3, you'll see that n equals 3. N equals 3 doesn't work. My 3's and 5's are horrible, guys. I'm sorry. So n equals 3 doesn't work. And why? So 4 factorial times 10 to the power of 3. Or 10 to the power of 4, I meant to say. But that is not going to be bigger than 10 to the power of 6, because 4 factorial is 24, and 24 times 10 to the power of 4 is not going to be bigger than 10 to the power of 6. So then, in the end, we get n is equal to 4. So basically, you have to have at least a fourth degree polynomial, Taylor polynomial, to get an approximation of sine 0.1 to be within an error of 10 to the power of -6. So I'll just repeat that just so it's more clear. So again, we need to have a Taylor polynomial at least of degree 4 to be able to approximate sine of 0.1 within an error, so that your biggest error is 10 to the power of -6. Okay, hopefully that makes sense. So let's go on and look at the next question. And if you guys, if you ended up on my channel, not because you're here for side one, but just because you found it, I would be very happy. But when I say the next question, we just have a problem set, and so I'm going down that problem set. But so next question, which is the third one, and in our problem set, the way the third problem is, it's like this. So you have root of 1 plus x minus 1 plus 1 over 2 x minus 1 over 8 x squared. Absolute value is smaller or equal to 1 over 16 x cubed. So then over here, what happens is that you can kind of see that this is the Taylor polynomial. It's of the second degree, because you have x to the power of 2. And then your function that you're kind of trying to guess, quote unquote, is this one. It's root of 1 plus x. So then the actual question says, show that this is true for all x greater or equal to 0. For all x greater or equal to 0. X greater or equal to 0. So basically we're saying that the second degree polynomial for all x is centered around 0. The reason I know it's centered around 0 is because it's just x. If it was centered around something else, it'd be x minus that x null. So centered around 0 is always within this error bound of estimation. So the way we can do that is, again, what we're going to do is we're going to remember how we find the error bound, which is we take the n plus 1 derivative f of x multiplied by x minus x null to the power of n plus 1 over n plus 1 factorial. And basically what we're going to do is we are going to kind of show that this, when you have n is equal to 2, goes to this. So again, as we said, we know that n is equal to 2 here. It's good to know. X null is equal to 0. X we're going to kind of keep because we know. And so now our mission's kind of done. We basically have all the info. We just need to solve the f plus 1 derivative of f and see that it is in fact 1/16. So let's do it. So we have 1 plus x to the power of 1 over 2. And the reason I'm writing it like this is because it's easier to then take the derivatives of it. So 1 plus x to the power of 1 over 2, that's our f of x. So then f prime of x is equal to 1/2 times 1 plus x to the power of negative 1 over 2. And then f double prime of x is equal to negative 1/4 times 1 plus x to the power of negative 3 over 2. Then finally, f triple prime of x. It's a triple. Okay. Whoever got that, I'm sorry. So it's going to be 3 over 8 times 1 plus x to the power of negative 5 over 2. So negative 5 over 2. So now what we're going to do is, again, as usual, we are trying to see what the maximum error is. So we're thinking of, well, what's the biggest error? Now, you can say luckily for us, this 1 plus x to the power of -5/2 is a decreasing function. So it's a decreasing function. The bigger your x is, the smaller f of x is. So we got our bounds are from 0, including to infinity. And so we know as x increases, our function is going to become smaller. So our biggest value will happen at 0. So if x is equal to 0, the third derivative of f of x will produce the biggest value. So then what we do is we plug in 0, we get 1 to the power of -5/2, which is just 1. So then f at 0, or that's where f triple prime at 0, which is our biggest value, is going to give us a value of 3/8. Perfect. So now we have that. Now we can go back and plug in all the information we need and have into here. So we get 3/8 times x minus 0 is x to the power of n plus 1, which is n plus 1 is 3 over 3 factorial. So then the 3 and the 3 cancel out, and all we're left here is, because 3 factorial is 3 times 2 times 1, but the times 1 doesn't do anything, guys. Small secret. So then we get 2 over here. So that is equal to 116 times x cubed. And look at that. It's like magic. It matches up with what we did. And that proves that the error bound is always going to be smaller or equal to 116 times x cubed. So then the next part of this question, what it asks is, it says find a fraction that estimates square root of 1.1 and show that the error is at most 1 over 16,000. Okay, so let's do that. So what we can do is we can see that root of 1.1 is the same thing as root of 1 plus x. Or I kind of spoiled it, but it's the same thing as 1 plus 0.1. And that, if you can see, it's actually just, you can kind of think of it as root of 1 plus x, where x is equal to 0.1. And just now, we kind of had an estimation. We had our Taylor polynomial, and we had the error bound. So what we're going to do is we are simply, very, very simply going to plug in 0.1 into our equation. So our Taylor polynomial over here is 1 plus a half of x minus 1/8 x squared. So if we plug in 0.1, what we're going to get is 1 plus 1 over 20 minus 1 over 800, which is equal to 839 over 800. And our biggest error is going to be 1 over 16 times x cubed. And we know that because it's right over here. We just proved it. So it's 1/16 times 0.1 cubed, which is equal to 1 over, guess what? It's 16,000. Woo! We got it. So it's 1 over 16,000. So there you go. We just answered. We proved that we estimated the value, and we proved that the biggest error that it can have is 1 over 16,000. And we're on to question 4. We're almost there, guys. We're almost finished for this one. I'm actually going to split this problem set into different pieces, more bite-sized, so I can get it out to you, and you can, if you want, you can take a look, and during that, I'll be creating the others. Okay, so last and final question is f of x is equal to 1 over cube root of 1 plus x. So the first question asks, find the Taylor polynomial p2 0 at x for f of x. For f of x. So we know what our f of x is, and basically what it's asking us is find the second degree polynomial centered at 0 for f of x. Let's do it. So f of x is equal to that, so I'm just going to dive straight into it. So f at 0 then is equal to 1. Yay! Then we need f prime at x, and that is equal to 1 plus x to the, well, it's not equal to that, but f of x is equal to 1 plus x to the power of negative 1 over 3. So then f prime at x is equal to negative 1 over 3 times 1 plus x to the power of negative 4/3. So then if we evaluate f prime at 0, that is just going to equal to negative 1/3, because 1 plus 0 is 1, and then you take that to whatever power, that's what gives you 1. Finally, f double prime at 0 is going to give us a result of 4/9 times 1 plus x to the power of negative 7/3. And again, if we plug in 0, all the result we're going to get is 4/9. So we have all the info we need. Now we just need to write it out. So P2 0 of x is equal to 1 plus, or in this case, it's minus. Watch out, because it's negative 1/3 times x plus 4/9 times x squared over 2 factorial. And again, if we want, we can simplify that quickly. 1 minus 1/3 x plus 2/9 x squared. And there you go. We have our Taylor polynomial. So the next part of it asks, use P2 is 0 at 1/3, so the Taylor polynomial at 1/3, or to write a fraction that estimates f at 1/3 is equal to cube root of 3/4, then show that the error in the approximation is at most 14 over 2,187. So what we're going to do is, so f at 1/3, we can right away see that f at 1/3 is cube root 3/4. So that's what it is. I wrote horrible 3 as usual, so it's cube root 3/4. And then what we can do is we can plug in 1/3 into our polynomial and see what we get. So the approximation for this is going to be 1 minus 1/3 times 1/3 is 1/9, plus 1/3 squared is 1/9 times 2/9 is 2/81. And so then the approximation is 74/81. So that's our approximation. And now what we need to do is we need to show that the maximum error is in the question it said 14 over 2,187. So as usual, we know that our error is fn plus the nth plus 1 derivative of x times x minus x null to the power of n plus 1 over n plus 1 factorial. So the n in here, we have the second degree, so we know instead of n, we're going to be plugging in 2. Our x null is equal to 0 because we're centering it around 0. Our x, in this case, we can already kind of see it's going to be equal to 1/3. Why? Because our interval is from 0 to 1/3. Because we're trying to estimate the 1/3 value using the Taylor polynomial centered at 0. So to maximize this, we know our x will equal to 1/3. And finally, all we need to do is we need to figure out what the nth plus 1 derivative is. Ooh, let's do that. So right over here, we have the second derivative. So now all we have to really do is take the third derivative. So f triple prime is equal to negative 28/27, 1 plus x to the power of negative 10/3. So right over here, you might see that it's a negative, but don't forget that your negatives don't really matter because again, I said in the beginning, but I'll say it just now again, that when you're really thinking about it, it's again, you can replace it with k, but it's always absolute value. So you're basically taking the absolute value of this to get the maximum. So the negative over here cancels out. And then again, our range is 0 to 1/3. So to maximize this, to make this biggest, you would plug in 0. Because if you plug in 1/3, a better way to show this is not by saying you plug in 0, but by again reminding us that this is a decreasing function because it's going to be 1 over something. So as this becomes bigger, the value becomes smaller. So because it's a decreasing function, 0 is bigger than 0 would provide a bigger value than 1/3. So that's why we're plugging in 0, we're getting in 1. So basically then the result we're going to get is 28/27. And it's not negative 28/27 again because we're going to have those absolute values there. Finally, we have all the information we need. So fn plus 1 derivative at x is equal to 28/27. So then we can plug in everything in. So 28/27 times 1/3 to the power of 3, because that is the 2, over 3 factorial. And that is going to give us 14 over 18 times 27, which by a huge surprise is 14 over 2187, which is exactly what we're looking for, because that's our error bound. And that's it. So these are your Taylor polynomials, and the error bound you can get because of the Taylor inequality. Hope this helps, and I'll be coming at you with sequences soon. See ya.